Good afternoon. Welcome to this EFG webinar on natural hydrogen in the Monzón-1 well, Ebro Basin, northern Spain. My name is Nikolaos Koukouzas. I'm the coordinator of the European Federation of Geologists Panel of Experts on CO2 and Hydrogen Geological Storage, and I will be the host of this webinar. The European Federation of Geologists is periodically organizing webinars to foster the professional development of fellow geologists and also to increase public awareness of the importance of geoscience. I'm delighted to present Christopher Atkinson. Christopher has over 35 years experience in the energy resource sector, working for both major companies, Shale and Arco, and developing and arranging financing for his own and associates ventures. He was the co-founder of PDA Limited, which went on to become Serica Energy PLS in 2004, and was also a founding investor in several other successful E&P startup ventures between 2006 to 2016. In 2018, he co-founded Helios Aragon, which is exploring for natural or gold hydrogen helium gas in Spain and other countries. He currently serves as a non-executive director of Rex International Holdings and as a board member for their subsidiary companies Lime Petroleum Norway and Masirah Oil in Oman. In 2020, he was elected to the board of Far East Gold, which is an eco-focused miner exploring for gold copper in Indonesia. Christopher has a highly successful track record of building and financing startup energy and resources ventures with multifold returns to the shareholders. He holds both a BSc and PhD in geology from the University of Wales, Swansea, UK. Christopher, please, you can start the presentation. Natural hydrogen in the Monzón-1 well, Ebro Basin, northern Spain, when you are ready.
Thank you, Nicholas. Thank you very much. Good afternoon, everybody. I imagine everybody's over in Europe. I'm based here in Singapore. I'm the chairman of Helios Aragon, and I'm going to give this presentation, obviously, on behalf of the company. And as Nicholas has pointed out, we're going to discuss the subject of natural hydrogen, and in particular, its presence within the Monzón-1 well in northern Spain. The webinar will be split really into two parts. Part one, I'm going to give an overview of what we call natural hydrogen, and this has been termed either gold or white hydrogen. I'm not going to go into this terminology in this talk. And in part one, I'm going to remind people that natural hydrogen does in fact exist, and this may be a factor which is known by many, but we can discuss it a little bit. I want then to look at geological factors which probably promote the accumulation of natural hydrogen. And then I want to say something about the exploration potentially for natural hydrogen in general terms, how we might utilize expertise from the oil and gas industry to help us search for natural hydrogen. The second part of the talk is going to be more specific to the Monzón-1 well. I'm going to look at the evidence for the presence of hydrogen in the well, the reservoir, the seal, the trap setup in the feature and in the structure. I'm going to go a little bit into a study that we conducted last year as a company where we looked at hydrogen seepage in the surface in and around the well. And then finally, I want to summarize what we consider to be an existing discovery of natural hydrogen present in the well. And then the webinar will finish with some conclusions. So first of all, natural hydrogen. If I'd have been giving this talk earlier, probably around 2020, and people had Googled the subject, does natural hydrogen exist? You would have got something like this to say that actually natural hydrogen doesn't exist, which I was very disappointed when I looked at that, because I'd been there by that time starting to look and find information about natural hydrogen, and it clearly did exist. So this was rather confusing. And as I said, unequivocally, natural hydrogen does exist. There are literally hundreds of examples of natural hydrogen seeps throughout the world. It's been recorded historically from as long ago as 2,500 years ago, with the picture you can see on the right here, which are natural seepage of hydrogen, not completely hydrogen, but fairly rich in hydrogen in Kimera in Turkey. And this has been known about for 2,500 years. More recently, 200 years ago, Los Fuegos Eternos on the side of a volcano in the Philippines, that was seen to contain around about 40 to 45% natural hydrogen. And in 1888, we have the first recorded analysis of hydrogen within a natural gas. So it is strange. We've known about the presence of natural hydrogen as a free molecule for a long, long time. But even until recently, people didn't think that it actually existed. And I think the important point is that the concept of natural hydrogen existing is embryonic. And right now, there isn't really an exploration strategy nor a resource assessment methodology which you can employ to go and successfully look for this gas. So why is natural hydrogen thought not to exist? Well, one of the biggest problems, of course, is hydrogen is the lightest of all elements. It's the only element to escape from the Earth's atmosphere. It diffuses rapidly in air, it's highly reactive, and it's rapidly consumed. Consequently, you don't stumble across hydrogen. You have to probably go looking for it. And therefore, there's a lot of existing prejudice, as I just said, that free hydrogen either doesn't exist or it's rare. And so if no one goes looking for it, no one finds it. Now, I say that because in certain parts of the world, people have looked for natural hydrogen, especially in countries such as Russia and in the former Soviet Union countries. There was a lot of looking for the presence of hydrogen. I'm not going to discuss that today as to why that is, but it's an interesting story, and it's to do with how one looks at the evolution of the Earth from its initiation. More recently, I think the big turning point was the discovery of trapped natural hydrogen in Mali. And this cross-section here is from the Pyrenees Basin in Mali, where people drilling a water well accidentally discovered hydrogen gas very close to the surface. It's actually, if I try and point it out here, it's actually here. It's within 1,000 meters of the surface. And the hydrogen there is about 98% hydrogen within the gas, and it's trapped below, of all things, doleritic sills in sandstone reservoirs. And this actual hydrogen is extracted commercially. It powers a small power station. And so far to date, although there hasn't been a large amount of production, the pressure in the reservoir and the pressure in the field is maintained itself to be roughly the same. And so it looks like it's constantly being replenished. So we know it exists. Natural hydrogen does exist. And I suppose if it does exist, what sort of specific subsurface conditions are needed for it to accumulate? And given the fact that I'm an oil and gas geologist by background, I've sort of lent on my hydrocarbon experience to think, well, okay, what would we require in the subsurface to allow for an accumulation of natural hydrogen? And I apologize, this is a very basic cartoon on the left. It was made for a financial presentation. But if we borrow from our understanding of hydrocarbons and how they form and how they migrate and how they accumulate, one thing you're going to have to need to start off with is a source of hydrogen. And we've known quite a bit about sources of hydrogen in the Earth. Hydrogen can be created biogenically, it can be created via chemical reactions, and it can also be generated by radioactivity. And so we know we can generate hydrogen in the Earth. We should probably look to find a reservoir. This gas will move, it's highly buoyant, it's highly mobile, and we'd like it to become trapped and accumulate in a rock which is porous and permeable, and therefore would allow the gas to be extracted. The third factor, and I think this is a critically important factor, is the presence of a seal. It's Helios's belief that this seal has to be very, very good. Shales probably would be okay. Evaporites would be probably better, and potentially the best seal is likely to be halite. And we think that's a very, very important factor in allowing for the trapping and accumulation of the gas. And the fourth factor, because of its reactive nature, is that ideally you probably would look for the presence of natural hydrogen below probably 2,000 to 3,000 meters below the Earth's surface, essentially where oxygen is absent, because in the presence of oxygen it will react because of its highly reactive nature. And so the accumulation, like I said, of natural hydrogen probably shares many similarities with those of hydrocarbons. And so how to explore? As I said, I think we should just really follow the hydrocarbon route. And we've been exploring for hydrocarbons now for well over 100 years. But in the very beginnings, we used route one, and that is that we tended to go and look at surface seepage of oil or gas, and that was where we tended to concentrate our attention. This is exactly the same in the case of hydrogen. For instance, on the left here, I illustrate a recent research project which has been put in place by IFP, where they are looking at trying to define surface seepage of hydrogen. In this case, they were actually looking to quantify seepage of hydrogen above things called fairy circles. I'm not going to go into the discussion of fairy circles in this talk, but they are geomorphic features on the surface, which are circular features, which are thought to be the result of hydrogen escape. So surface seepage would be probably the first thing to look for, and you would go off and you would map those seepages, look for the concentrations of hydrogen, look at where anomalies may exist, and that might give you a guide as to where you should go looking. The third way, and it's the way that we're going to talk about it in Monzón, is that, of course, fortuitously, somebody might have actually been drilling a well into the earth and actually found hydrogen previously. And that is the case, as I say, in Monzón, which we will discuss. So you could start to look at existing wells. The problem here is that generally where wells for hydrocarbon and other resources have been drilled are not necessarily the place you'd go looking for hydrogen. But as I say, it's probably a good starting point. With this information, you then just combine that with good geological, geophysical subsurface data and quality interpretation. You'd look to generate some sort of subsurface prospect. And you would then, no doubt, go on to drill a concept testing well to see if the hydrogen gas is there and if it can be even extracted. Now, I say all of that, it's never been really done, although people are trying to do it at the moment. But that's probably a fairly simple approach to how you would go about exploring for natural hydrogen. Now let's talk in detail a little bit about the Monzón-1 well. The Monzón-1 well, here's a map of Spain. And what I've done is I've illustrated in yellow outline there the province of Aragon. And the Monzón-1 well is located in the northern part of Aragon, actually immediately south of the Pyrenees mountain front. And it's at the far northern end of the Ebro Basin. The cartoon to the bottom right is a north-south cross-section, very, very simplified and very cartoon, where you have the South Pyrenees thrust belt immediately to the north of the well. That thrust belt terminates in a feature called the Barbastro anticline, which is a complicated zone of deformation at the very end of the southern Pyrenean thrusting. But the Monzón-1 well is located in the Ebro Basin. It does not involve with any thrusting. The thrust belt exists to the north, and the well penetrates down through a very thick sequence of oligomycene molasse and down into an autochthonous succession of Triassic and Jurassic rocks which sit on basement. And this is the cartoon representation of where the well would be located. Hydrogen was actually found, and we'll look into this now in more detail, in two locations: shallow up in the tertiary in the oligomycene, but more importantly down deeper in the Bunter Triassic sandstone. The well, as I said, was drilled by a company called Empasa in 1963. It was drilled to explore for oil and gas, which it failed to find, but it encountered significant hydrogen shows when drilling, as I said, in two locations. And I'd like to show you those two in a little bit more detail shortly. First of all, let's just look at the stratigraphy of the well. On the left-hand side is a columnar section through the well. And if we start at the base of the well TD'd at 3,715 meters below ground level. It actually TD'd in conglomerates belonging to the Bunter, the lowermost part of the Triassic. It was only a short distance above the basement. We can calculate that from looking at seismic data. And what you had above the Bunter was the classical tripartite series of the Triassic. You had the overlying carbonate-rich sequence of the Muschelkalk, and then the more evaporite-rich sequence and shale-bearing sequence of the Kuiper. And then there is a thin interval of lower Jurassic in this area called infraliassic, and then a major unconformity which separates the Mesozoic from the Tertiary. And you then go into a succession, first of all, of Eocene sandstones, but largely a very, very thick sequence, as you saw on the cross-section, of Oligomycene sandstones, conglomerates. But a very important interval here, actually also of halite, which is part of the nearby Barbastro anticline. The hydrogen shows, as I said, the most significant ones and the ones we're going to talk about exist right down at the bottom of the well and in the Bunter sandstone. And the Bunter sandstone is around about 55 meters thick in this well. And I think it's important to note that it's overlain by many different lithologies and intervals which could act as seals to stop hydrogen vertically migrating through the area. Immediately above the Bunter is the evaporite-bearing Bunter Shale. That's a total thickness of 185 meters. You then have a 60-meter interval of Bunter halite, which is, can be termed the rot halite. That's what it was termed in 1963. You then have an interval of Muschelkalk and Kuiper, as I've described, and within there you have halite and you have evaporitic-bearing shales. That's in excess of 0.5 kilometer thick. And by the time you get up into the top section here, at this interval here, you have 1,000 meters of tertiary aged halite and evaporite. So vertically above the Bunter sandstone interval, you have around about 1.7 kilometers of excellent sealing lithologies within this well. And I think that's very, very important to note. If we look at the actual evidence for the hydrogen, as I said, there was two intervals. The upper interval here, which occurred at around 480 meters when drilling, is up in the Oligomycene in a few thin sandstones. Total gas of about 0.4 to 1.2, which was determined to be pure hydrogen. However, the important one, which I've mentioned, is the one at the very bottom of the well in the Bunter sandstone. This interval was very significant. Total gas of 25%, which is a very, very large show by anyone's estimation. And again, it was determined to be 100% hydrogen at the time of drilling. Now, anybody out there who can help us with this, the hydrogen was detected using what appears to have been called a Prackler system. We have searched high and low to try and find some form of mud gas system, which was called a Prackler system. We've been unsuccessful, but if anybody out there recognizes this term and could help us, we're none the wiser after several years of trying to find out. All that we have is the end of well report, which discusses the presence of the gas, but we don't know by which detection method it was used. We're assuming it's some sort of mud gas detection system manufactured probably by a company called Prackler. Now, if we look at the Bunter Reservoir, the well itself contained a fairly basic log suite. It contained a gamma ray neutron. It contained 2 lateral logs for resistivity measurement. There was a sonic log and a caliper log. And having said it's quite basic, there's enough information there to do detailed log analysis. Helios has conducted detailed log analysis on the Bunter with very favorable results. And the yellow interval here is the Bunter sandstone at the bottom of the well, very, very sand rich. The net reservoir interval is calculated around about 55 meters. The net pay within that 55 meters is about 30 meters, with an average porosity of about 9.5%. And the average water saturation in the pay is about 36%. In other words, a gas saturation of 63%. We've tried everything we can to remove gas presence from this well by changing salinities, altering rock factors. No matter what you do, you always end up with an interval of gas in the Bunter of some type. Now we're suggesting that this gas is hydrogen only on the fact that we have show information which said that it was 100% hydrogen. But I said there is a presence of a gas column. We pretty much can determine that directly from the logging parameters. And it was even mentioned in the end of well reports at the Monzón-1 well that the presence of this interval of gas, but unfortunately it was hydrogen. And in 1963, there was no economic value for hydrogen. And it's probably why this interval actually wasn't flow tested, because the pattern in those days in the early 1960s was to flow test anywhere that they had shows, but they did not flow test this particular well. Overlying the Bunter is the Bunter Shale. And I think this, from our mapping to date, has to be the initial feel of the accumulation. And the Bunter Shale here is, this is a different scale, but this is the top of the Bunter sandstone, the yellow at the bottom. And then you have this 185 meter thick interval, largely of shale and some siltstones, but it's mainly shale and mudstones, a couple of thin sandstones. And at the very top, this green interval here is the rot halite, the 60 meter interval of halite at the very top. This is a pretty good seal. It contains quite a few zones of anhydrite and evaporite. As I say, there's one or two little zones which, according to the log calculation, have some sort of gas saturation within them, but largely it's a pretty good sealing lithology. And so it's our view that we have a reservoir, which you can see down at the bottom here, which is the Bunter, and this is overlain by a very thick sequence of shale and interbedded evaporites. And we believe that the Monzón-1 is actually really an untested gas discovery. There's calculated gas down in the Bunter. The shows suggest that it's hydrogen, but it was never flow tested at the time. One thing we did in 2022 last year was that we went out and tried to ground truth the presence of hydrogen in and around the Monzón-1 well, and we did a soil gas geochemical survey. It was quite intensive. There was a lot of sampling points. We followed the standard procedure. It was conducted in association with a company from Denver in America. We had a steel sampling probe with a capillary tube. We collected samples once this probe had been pushed into the ground, about 1.2 to 1.5 meters. We collected two samples. One sample was actually analyzed immediately. We had a portable mass spectrometer, which we set up in the local town. And in the evenings, we used to run the analyses of the samples that we collected during the day. And then another set of samples were returned to a laboratory for a later analysis. And if we then now look at the results of that survey, this is the sort of surface geology of the area. And this here is the location of the Monzón-1 well. On this particular map, we've just put on concentrations in parts per million of hydrogen and helium, hydrogen in red, helium in yellow. And one thing that's interesting is we definitely have an anomaly above the Monzón-1 well, which I think is probably correct because after all, we have drilled a 3,700 meter hole down through the geology into the earth. And even though this hole was abandoned by being cemented and abandoned properly, it's highly likely it could act as a conduit for gas escape, especially something as easy as hydrogen to escape, and also helium. So we have a significant anomaly over the Monzón-1 well, actually over the crest of the structure. We also have anomalies to the east-southeast of the well, and this is interesting because this is an area where we see a gas chimney on the seismic, and we see gas effects of gas leaking from down at the Triassic level up to the surface. And this sits just off the Monzón structure. We also have anomalies here, which are on the southernmost Pyrenean thrust. It's the last thrust, the thrust that exists on the northern limb of the Barbastro anticline. But in many other areas, we had no anomalies, just background. And like I say, we collected a lot of data, and we're quite comfortable that we're seeing hydrogen concentrations above the well. So in summary, and this is the only seismic line I'm going to show in the talk. This is a north-south line through the Monzón-1 well. This is the well here. It's been colored in, it's been interpreted mainly for presentation. The yellow is the Bunter level, which is where we feel the gas, the hydrogen is reservoired. The orange is the Bunter Shale. And the pink here is actually the rot halite. But this is the structure that's of interest. It's a large basement-defined structure. It was identified in the early 1960s, as I said, in oil and gas exploration. It's present both on seismic and gravity data. It's not subtle. This is a very obvious four-way closure. And if we use this to sort of summarize what we think we've got at Monzón, then we think that the source of hydrogen here is probably coming from deeper in the crust and from the upper mantle. And we think this is being delivered by a fault system, which actually exists to the east of where the well is drilled. And it's these faults which set up the basement structure. And these are very deep-seated faults. They go down deep into the basement. They reveal inversion during the later compression associated with the Pyrenees mountain building. They are inverted. But these faults are deep-seated faults. We think that the hydrogen has migrated up these faults and into this structure. And that the reservoir, as I mentioned, would be the Bunter sandstone, and that the overlying Bunter shale, given when we map the top of the reservoir, the closure has to be defined by trapping at the Bunter shale level. It would be too big if we were to look and use the rot halite. And in any case, there's no reservoir within a closure mapped at the rot halite level. The closure would be down at the Bunter sandstone, and the trap would be defined by the Bunter shale. And the other obvious thing is that this well, the gas in the well, or the presence of the hydrogen in the well, is around about 3,600 meters, which is way below the level that we think we need to be at to avoid the presence of oxygen. So as I said in a summary, Helios believes that this was a hydrogen discovery. We think that that it's there waiting to be rediscovered. And to just give some conclusions to the webinar, we strongly believe that natural gold or white hydrogen exists, and it occurs extensively throughout the world. We believe that under favorable geological conditions, just like gas, oil, it can be trapped, and it can be trapped in the subsurface. The one thing here that we think will be very important is seals. You've got to have what we think would be good to excellent seals to achieve that. We think that you can use existing hydrocarbon exploration techniques to help to locate those traps, and we believe that the Monzón-1 well in 1963 actually records the discovery of natural hydrogen, which was made when actually at that time the hydrogen was not being looked for. And it's Helios Aragon's contention that this dry hole in the hydrocarbon sense, could be a very important component in the largest energy transition the world has ever seen, as we move from oil and gas to other forms of cleaner energy. Now, Helios's plan is a very simple one. It's a very simple failure leg. We would like to go ahead and once all permissions are in place, and we will re-drill the Monzón structure, and we will test the structure and try and see if we can establish a flow of natural hydrogen from the reservoir, just like in Mali, with the aim, of course, of making this a commercial venture. And that, ladies and gentlemen, concludes the end of my webinar. Thank you.
Yes, thank you very much, Christopher, for this very interesting presentation. I think we have some minutes to answer some questions. We have we have received a question in the webinar chat. I can say to you right now, and we have received also 5 questions in the Q&A. So the first question is, please let us know what was the hydrogen content in the gas during testing, and what is the hydrogen contents at the surface according to the geochemical survey. If you want to answer this one.
The geochemical survey that's well, I gave you the results there of the geochemical survey. You could see that the results were pretty much obviously delivered in parts per million. With regards to the actual well, there was no flow testing of the Monzón-1 well. All that we have is the information that was determined at the time of drilling that must have been some sort of mud gas detection system, and which indicated and strongly implied that this was hydrogen. And we don't have the records of the actual mud gas. The mud log has not been preserved from this well. We've searched high and low, it doesn't exist. All we have is the interpreted results at the end of well report. And I say one of the key things would be to understand what exactly was the Prackler instruments that this measurement was made from. That would be a very important starting point for us to maybe work out, you know, whether or not this was pure hydrogen. I think we suspect that it's almost certainly going to be associated with some other gases. Just to give you an idea, Monzón was not the only well in this area which encountered natural hydrogen. There was 2 other wells that have also got, unfortunately, I can't tell you where they are. There's 2 other wells, and they have analyses which indicate that also nitrogen was present in association with the hydrogen, and also argon. So whatever was going on here in the 1960s, they had some sort of reasonably sophisticated gas detection or gas analysis system at the well site, or samples were being analyzed, because we do get quite detailed results on gas shows and gases that were encountered while drilling.
Thank you very much, Christopher. Another question is the following. Did you run noble gas isotopic analysis to pinpoint the origin of helium and perhaps hydrogen?
No, we haven't. That's something that we'd like to do, but we have not done that yet. No, we haven't. Yeah, okay. I could see why would want to do it. Yeah.
Thank you. Another question is, at basement level, the anticline appears to be underlain by an inverted basin. Was hydrogen produced in this shallow meta-sedimentary basement level or deeper?
It's difficult. If somebody out there knows what the basement is below where we are, I'd like to talk to them. When you look at the seismic data, it's not crystalline basement exactly there. It looks like to be metamorphosed, semi-metamorphosed material which forms the basement. I don't really know. We don't really know a lot about what the basement is, but there may be people with better knowledge than me of what the basement configuration of that part of the Ebro is. And I would welcome an interchange on that, because we don't know a great deal about that.
Yeah, okay. Another question, if hydrogen shows in the tertiary and at surface are due to top cellular failure and vertical leaking from Bunter, then it is good or bad news?
Yeah, exactly. I mean, I mentioned the gas chimney that we see on one of the lines to the east-southeast of the well. There we see very, very interesting brightenings up into the tertiary above faults, which could indicate that gas has got up into the shallower levels and perhaps migrated a little bit laterally in some of the more porous or permeable intervals. It's obviously a risk. I suppose what drives us to believe that you know, maybe the gas is trapped there is the high gas saturations that we see on the logs down in the Bunter. Seems to indicate it doesn't look to us to be residual. It looks to be potentially, you know, reservoir and pay. But at the end of the day, I don't think anybody's going to work this out until we're able to just re-drill the feature and collect a proper data set.
Definitely. Another question is, maybe Prackler manufactured some gas chromatographs besides standard normal gas chromatographs?
Yeah, Yeah, I mean, I am aware of the German company Prackler Seismos. We used to be the seismic company. We've tried to find people who, but the people we know on the seismic side had no knowledge if they ever made a gas detection system for drilling. And again, if anybody has any information, we'd love to hear from you, because we've drawn a complete blank on what that can be.
Yeah. That's right. Another question, how reliable were the chromatographs in the early 60s for hydrogen? So back to history.
Again, if we knew what the chromatograph was, and we could maybe answer that question. It's difficult to say. When you read the post-well reports, not just in this well, but as I said, in 2 others, it's pretty clear that the people drilling this well and analyzing the gas were pretty convinced this was hydrogen, and they were surprised. In fact, they used terms strange, and they were looking for, at the end of the day, were looking for oil and gas, oil and methane, and this was an anomaly for them.
Yeah. Another question is, have you identified a gas-water contact in the well?
Doesn't appear to be one where we are. If you saw the log there, I mean, the problem is the logs end before logging suite doesn't go all the way to the TD. But in the logs that we've got, we don't appear to see, if you believe our interpretation, a water leg at that point. Yeah.
Another question: Could you please explain the mineralogical background of hydrogen production at this Monzón site? What kind of mineral reaction are expected?
Again, I mean, we're using direct detection here. The reason we got into this project was just looking at this well for other reasons many years ago, and it stuck in my memory. The presence of hydrogen, it was a bit weird. I didn't really understand it, and so as to where it's come from, that's a difficult question. I have got a slide here. Let me just go on to the one thing is that the Pyrenees, for some reason, is interesting in that there does appear to be natural hydrogen seepage associated with the Pyrenees, especially the northern side of the Pyrenees. And there's been a lot of work done by French scientists. Here you can see Lefebvre 2021, who document the presence of natural hydrogen seepage along the North Pyrenean frontal thrust and along the North Pyrenean bounding fault. And the conclusion there is that why the Pyrenees might be of interest is just because the collision history of the mountain belt, the fact that the collision is slightly oblique, and the fact that the mantle doesn't behave like it should do when you get the collision. The mantle tends to stay up and becomes wedged and abducted. So you get mantled material close to the surface. And of course, mantle material through a process of serpentinization is a potential source of hydrogen. Whether or not you can use that argument in the southern Pyrenees, this is the area I'm talking about. This is the geological map of the Pyrenees. There's the Cantabrian Mountains over the west. This is the Pyrenees. This is the area we're talking about here. And this is the area where there's been a lot of work on the presence of hydrogen seepage at the surface. And it does seem to be a phenomena that's quite common in the Pyrenees. And like I said, it could be something to do with just the way the Pyrenean mountain chain is formed. And there are probably much better qualified people out there to understand that. And we had a simple theory that, okay, in the northern side, you have the ability for hydrogen to leak along these major faults. There isn't a lot of sedimentary cover in the northern side, and the sedimentary cover is further to the north. Whereas in the southern side of the Pyrenees, which is where we are, there's a lot more Mesozoic, and there's certainly a lot more tertiary sediments which are preserved. And maybe if you are getting hydrogen generation, deep-seated hydrogen, there's more chance of it to be trapped versus here, where hydrogen escapes on the northern side. This is complete theory, not backed up by any evidence at all, just trying to understand why you would get hydrogen generation in this area.
Yeah, thank you. There is also another question related to Northern Pyrenees. It says as a statement that the Northern Pyrenees Thrust and Fault Belt, the CNRS Total Consortium indicated the presence of abundant hydrogen traces in several geological locations, but they link this with hydrogen with deep serpentinization, alteration of an exhumed upper mantle-lower crust in relationship with the lergolites that outcrop there. Any comments on that? Yeah.
No, that's true. That's right. I've been there. I've seen the lergolites. I know exactly. Yeah, I mean, that's what I was just trying to explain here. I mean, for some reason, you know, you do get natural hydrogen seepage in the northern side of the Pyrenees. It's clearly linked to what we've just discussed. Can you drag that argument to the south? I don't know. But you know, it's an area for research, put it that way.
Okay. Yeah. Another question is related to remote sensing. Did the remote sensing results of the SEN4 hydrogen project contribute anything?
Not at the moment, no.
Another question is about that sometimes drilling generates hydrogen-related bit-induced metamorphisms. Is that correct?
Yeah, no, I think the issue we have here is it's recorded over quite a big interval, and when you get that, it's normally a little bit thinner. We also, and I didn't show this, but we've also have a well actually in another part of the world where we see the mudlog response of a clear hydrocarbon bearing a clear hydrogen bearing interval. And the mudlog response is very characteristic. It's very different from the presence of, say, methane, and people puzzled over this for a long time. But there, it was assumed to be hydrogen, and that was over an interval of about 120 meters, which I think is too much to be just a drill bit flowing down, jamming, burning, you know, having a reaction at the drill bit. And the same thing here. These shows are recorded over a very long, over quite an interval, several meters.
There is a question about the permits. What kind of administrative permits do you need to do your prospect in Spain? Hydrocarbon law or mining law?
Exactly, that's a good question. I mean, that's all going on right now. These permits were actually awarded under the hydrocarbon law. In fact, as far as I'm aware, they're the last permits awarded in Spain. And actually, we got into this project primarily because of helium, and hydrogen was a secondary thing. That was many years ago. Hydrogen has now become the in vogue thing. And I know where people are going with this. The problem with hydrogen, natural hydrogen, is in many countries in the world, and Spain is no exception. There is no legislation governing how we could actually extract and develop it. And it's right now in Spain, we're part of the process with the government and with the Ministry of Energy. We've made a submission ourselves just before Christmas. I'm not sure if hydrogen is going to be covered under some modification of the hydrocarbon law, or it's going to come under a mining law. But our permits at the moment are under the existing hydrocarbons law.
Yeah. Another, again, question from geology. How did the hydrogen migrate to the Oligomycene section if the thick Triassic and low Tertiary is the ultimate seal?
I have no idea, other than, like I said, potentially we see southeast of the well, we see some shallow gas anomalies above faults. Maybe some gas has made its way up in those areas and may have migrated laterally into the area. Don't really know is the answer. Yeah.
Again, another question about the license. How hydrogen is treated by the Spanish administration, but I think you have already. Yeah.
It's in a bit of a gray area at the moment between one or the other. And
so another question, with 100% hydrogen, how did they not experiment explosion on the surface mud line? Was the mud weight so high?
The mud weight was very high. And it's a common factor. A lot of formation damage in these early wells in Spain. That's what's even more intriguing. The mud weight was quite high, but you still get incredibly significant shows, and they're way overbalanced, way overbalanced. And I think it was I've got the actual figure. I think it was, yeah, but the answer is yeah, very overbalanced drilling.
Yeah. We have a statement from a Spanish colleague saying that the government is now preparing a modification of the mining law. The EFG proposed through the Spanish Association of Professional Geologists to include a new chapter about natural hydrogen in the new law. So that's as a statement from a Spanish colleague.
Yeah, that's correct. And
yes. Another question is about, in your opinion, what is the source of hydrogen serpentinization? Why is there a common anomaly between hydrogen and helium?
The association between hydrogen and helium, I think that's just a general observation. I mean, we have one of our technical advisors at Helios is Professor Christopher Ballantyne, the University of Oxford in the UK. He's an expert on helium. And in fact, as I said, this was largely a helium project several years ago. And when we were talking to him, actually, when we began talking to him, the only thing we knew for certain is that we had hydrogen. And his immediate answer was, well, if you've got hydrogen, you'll almost certainly have some sort of level of helium. Now, I don't know if that's true worldwide, but he's a world expert, and his view was that the chances are there would be helium here. And I think it's just to do with the fact that if you can trap hydrogen, you will probably trap helium at the same time.
Yeah, that's probably. Another question is, what do you see as the likely source, rock for the hydrogen? Serpentinization?
I think, my commercial hat on, I don't really care where the source is as long as it's there. And I got a well that's found it. So, I think there's a lot to be done. If we can drill this well, and if we can test it properly, if we can extract the gas properly, there's a whole legion of other techniques that we can employ to try and look at the isotopes, try and understand what the origin of the gas is. Fully agree. I just don't think we've got enough information at the moment to say one way or the other where this would come from.
Another question is, do you think using passive seismic acquisition can help in exploration?
I don't know. I'd like to be convinced. Maybe again, somebody out there has. I'd be delighted. We'd be delighted to talk with them if they think that could play a role.
Yes. So another is, are there any other evidence of natural hydrogen further north in the Pyrenees? If not, what do you think makes Monzón area different than any other potential accumulation in the north?
Well, as I said, there's a lot of evidence for natural hydrogen presence in the northern side of the Pyrenees, especially along the North Pyrenean Fault. And in the southern Pyrenees, we know at least of 2 other wells, not near to Monzón, which have recorded the presence of hydrogen, natural hydrogen. So there could be more. Again, if people are not looking for it, then it probably hasn't been measured.
Yes. Another question is, did you find any report regarding a possible transparent flame from this gas?
No, didn't see that, no.
Okay. So I think, Christopher, we have received many questions. Actually, you already replied to over 20 questions from the webinar chat and another 7 questions, more or less, from the Q&A. So I think it was a good success, I think, for the time being.
Yeah, no, yeah. I mean, and please, anybody out there, please contact us. I'm sure we can get the contact details somewhere. We're delighted to hear from people. This is a very embryonic business. It's a very embryonic industry. There's good quality scientists, I'm sure, everywhere looking at this problem from different directions. And we'd be pleased to talk and pleased to hear. And
last question is, how much was delta hydrogen index from hydrogen gas?
Don't ask me. I probably would have to ask our geochemical expert, Dave Shenzian, who from Geochemical Insights, who ran the survey from Denver.
Yeah.
That's the sort of question David could answer.
Yeah. Now, so thank you very much for your presentation and for sharing your knowledge with us, Christopher. And thank you to all participants for joining us today. It was great to have you with us. Take care and see you at the next EFG webinar. Thank you very much.
Thank you. Thank you very much.